Well, welcome. My name's Canucci Taranella. I'm the executive director here at the Wenatchee River Institute. I am so excited to bring this night of geologic fluids to the banks of the Wenatchee. It is a great privilege to get to lead this organization, and I'm excited that you are all here to support it. In addition to myself and our great speaker, we've got Joshua on the digital platform, helping the 40 people who are online hear us tonight. And we've got another volunteer helping us serve. Sorry, I've got your name. But it's Virginia, thank you very much for being here. And Dave. As you know, the Wenatchee River Institute does community programming like this, Red Barn events. This Saturday, we have another Red Barn event on healthy bee habitats in your home garden, as well as a birding Red Barn event next week on the belted kingfisher, which should be a lot of fun. So make sure you find time for that. More things to learn all the time. In addition to community programs, we do youth education. We send educators as far away as Brewster. They left the house, they left the parking lot before 6:30 this morning, loaded up and took science on the road. So we support those traveling naturalists with your donations here, and when you think about us with your end of year donations. So it's great stuff. Great opportunity to have a facility like this and to have science moving around our watershed. So thank you for all of that. One of the most important things that I do here is acknowledge the people who were here first. So I'm going to do a land acknowledgement, and I'm going to read it directly off the card, so it is communicated in the way in which the Shin-Pei-Squaxin or Pisquosa people wanted. We are spreading the message they wish to be spread to the public. The land the Wenatchee River Institute sits on is the ancestral homelands of the Shin-Pei-Squaxin, the Pisquosa or Wenatchee people. The Shin-Pei-Squaxin, meaning the people in between, had villages positioned along the Wenatchee River and surrounding areas. Their ancestral homeland extends from the Cascade Range throughout what is now known as the Wenatchee and Okanagan Valleys. The culture and economy of the Shin-Pei-Squaxin people centers on taking care of the land. They fish, hunt, gather roots and berries, basket-making materials, and medicines. The Shin-Pei-Squaxin are named within the Yakima Treaty of 1855. Language to establish the Wenatchee Reservation was never followed through, even with the needed surveying completed. Many Shin-Pei-Squaxin now live on the Colville Reservation, 150 miles northeast of Leavenworth. They were forced off their lands here, and the U.S. government moved them to this reservation. The Shin-Pei-Squaxin people are still alive today. They continue to practice their culture, harvest their traditional foods and medicines, and hold their ceremonies passed down from their ancestors. Most people won't see or notice them, but they continue to be on the land they are connected to. Their traditional language is Inham Sheen, which is an interior Salish dialect, and we would like to welcome you all by saying hello in their language. Tilhusht. We offer this land acknowledgement as the first step to amplifying Indigenous voices and recognizing the harm done to them as a people. We stand as an ally to recognize their connection to the land and their rights to practice their culture on these sacred lands. We encourage all to learn about the Indigenous peoples of the place you now call home. The Wenatchee River Institute is committed to sharing this land acknowledgement and following up with other actions to educate and be respectful. In addition to that, other folks that help us make this happen are our sponsors. So I'm going to share that list with you. We've got Gustav's Grill and Beer Garden, Ludwig's German Restaurant, the Obertal Inn, Posey Hand-Picked Goods, South Restaurants, Hotel Pension Anna, the Munchen House Restaurant, Sleeping Lady Mountain Resort, North Central Washington Audubon Society, and the Icicle Brewing Company. Additionally, we got the Cove Resort at Fish Lake, Cold Chuck Consignment, the Riverfront Rock Gym, Mountain Home Lodge, and Mitchell, Reed, and Schmitten Insurance. Whew, that's it for the commercials. Now, I'd like to welcome the Wenatchee Valley chapter of the Native Plant Society and Joan to introduce our speaker, please. Thank you. You get this.
Thank you. Hello. So many of you know who I am. I'm the chair of the local chapter of the Native Plant Society. My name is Joan Frazee, and I'm just really happy to see a big crowd here tonight. That's great to learn about geologic fluids. I'm excited to learn about that as well. Chapter news. We have one more program this spring in April, again here at the Red Barn. And thank you very much to Wenatchee River Institute for partnering with us, allowing us to host programs here in partnership with them, and also to provide the technology so that we can offer it out into cyberspace. That's a great thing. And without them, we probably wouldn't be able to afford to figure out that technology on our own. So we have another program in April 26th, about restoration with beavers. And then coming to your inbox in the next few days will be the next edition of Prairie Smoke, our newsletter. And in that newsletter will be field trips, at least to starter field trips for the field season. And so you want to make sure and pay attention to that. And if you're not a member of the Native Plant Society, I encourage you to pick up a brochure on the table there on your way out and become a member, because we do all kinds of fun stuff with plants. And we're going to learn about how important geology is to plants tonight, at least one aspect of it. And so without further ado, I will introduce Connie Maymill, our program chair, and she will introduce our speaker for tonight. Thank you.
Thank you, Joan. All right, well, I'm really happy to be able to introduce Dr. Ralph Haugerud tonight. And Dr. Haugerud received his Bachelor's of Science and Master's degree in geology from Western Washington University, and a PhD in geological sciences from the University of Washington. He joined the U.S. Geological Survey in 1986, where his work involved geologic mapping in the North Cascades, the Salish Lowland, and Central Washington. Then he became interested in digital topography in the early 1990s, and as a result of his great technical skill, he became the lead scientist for the Puget Sound LIDAR Consortium. And that was from 1999 to 2017. But really, Ralph considers himself a structural geologist. He watches the earth move. And he co-authored the book Geology of the North Cascades, which I have a copy of that here. And this is really a go-to guide for anyone who's in that region still. And Ralph currently lives in Wenatchee, so we're really fortunate to have him here. And thank you so much for being here tonight, Ralph. And I am excited to hear about geologic fluids and plant life.
Am I live, Josh?
We're all live.
I have a confession to make. I know almost nothing about plants. And when I was invited to give this talk, it seemed like
You need this.
I've got one right here.
Okay.
It seemed like it was important to say yes, but what can I talk about and not make a fool of myself? And so, well, you'll see what I've chosen. What I want to talk, well, I realize I've forgotten the first thing I was going to say. If you really wanted to learn about rocks and plants and how certain rocks make soils with certain chemistry that favor. Okay. We have a mic for the Zoom audience, and I've got to speak up for you guys here in the house. This is my wife, Martha, who knows well that I don't speak very loudly much of the time. We do a lot of. Is that better now? You guys hear me? Okay. If you really wanted to hear about how certain rocks make soils of certain chemistry and favor the growth of certain plants, you should have been here a few months ago when Ted Alway gave us a wonderful talk about just that. I do not know enough about plants or soil chemistry to do anything of the sort. So I'm going to talk about something different. I'm going to talk about a play on words, fluids, controlling fluids, and talk about how certain things that we don't always think of as being fluid, certain rocks actually flow, control the occurrence of the most important fluid for plant life, which is water. So my outline here, first I want to talk about an Art Krukeberg connection, which is why I think I'm standing up here. And some of you know of Art. He was one of the founding members of the Washington Native Plant Society. I want to briefly discuss, wow, okay. How geology is more than just rocks, and that some rocks flow. And then I want to talk about 4 geological fluids that have strongly influenced the availability of water to plants in north central Washington. And the first is the Earth's mantle. And Martha, can you hold up the smaller rock back there? This is a piece of the mantle, the stuff that makes up the Earth 100 miles down that happens to have been brought to the surface. And it's a dense, hard, stiff thing. And we have lots of good evidence that on geological timescales, it flows. I want to talk about basaltic lava, and I think we all know that lava flows, which has had some unusual, unforeseen effects as far as how moist or dry the hillsides around here are. I want to talk about glacial ice that made a landscape that has allowed us to irrigate much of central Washington fairly easily. Now, those aren't native plants, but they're important plants to us. And then I want to talk about air, which is also a geological agent. And because of air around here, we have a blanket of loess that mantles most of the landscape, which is very important for conserving and giving back water to plants in this environment. So as Connie mentioned, I went to the University of Washington for my PhD and spent 5 years there. She didn't say that the survey hired me, took me to DC and then to San Francisco for 5 years and sent me back to Seattle. And I spent 28 years living and working in the Orson Bennett Johnson Biological Laboratory, erected in the year of 1930 AD. Well, over the years, biology has gotten a little smaller and moved someplace else. And Johnson Hall is now the home of Earth and Space Sciences and Biology. And when our kids were young, I had to do my morning stint at the co-op day school. I worked in the afternoon, came home, helped with dinner, put the kids to bed, and went back to work at night to make up my hours. And I met this kindly gray-haired old guy wandering the halls. Now that I'm one of those, that's not so important that he was kindly and gray-haired, but this was Art Krukeberg, and we had conversations. We talked about lots of things, and I don't remember most of them, but he was interested in geology and about landforms, and I was too. And eventually one of my pictures made it into his last book. We're at the Yellow Star there at Leavenworth. And my wife's sister, Cece, who is sitting over there, knew this story and said, Ralph, you knew Art Krukeberg. You've got to come talk to the Native Plant Society about knowing Art Krukeberg and all the ways that geology influences plant life. And I had known that Art had written a book about this that I had not read. And so I said, Cece, do you have a copy of his book on geology and plant life? Maybe I should read it before giving this talk. And she said, yes, you gave it to me. And so I asked for it back, and I've read the first third, and it doesn't speak to me very much. But one of the things I got out of this book is this wonderful diagram that Art reproduced from an earlier study, showing the ways that the world is interconnected. And the basic point, and one of the major points of this book, is that everything is connected to everything. And in particular tonight, I want to talk about how geology, and I need to learn to use this pointer, geology is related to the availability of water, which conditions how plants can grow. That's my theme. So next point, of course rocks flow. When you look at a slab of gneiss like this, how could that texture have occurred in any method other than something flowing, continuously deforming? Of course rocks flow. Second point, rocks are interesting and useful, and we study them because they control landslides, they have gold in them, we can find coal, they're all about earthquakes. And a lot of that can be done by simply in a descriptive form, what is where. And you don't have to think about simply rocks other than as things that are. There's this rock on this hillside, this rock in that valley. And our culture reinforces that notion. We speak of the hills as being eternal. And geology is a playground, a palette upon which we play out our lives, which plants grow, species evolve, things happen. And that works. You can find gold. You can drill for oil and get successful. You can predict earthquakes that way. But rocks are more than that. Rocks and their spatial relations are the product of a history. They tell a story. And if you strive to understand that story, you can do a better job of finding gold and coal and oil and earthquakes. And you also make your life a lot more interesting. The world becomes a much richer place. How'd that happen? Why is this river over here and not there? How'd this rock get here? I'm not going to answer any of those questions, but those questions are what motivates me. My interest is in seeing the world as a living four-dimensional thing. The landscape is the current chapter in a story that's still going on. And if you look hard enough, you can figure out some of the earlier parts. So what's a fluid? And the answer is anything that continuously deforms, that is flows, under an applied stress, an external force. There are substances that cannot resist any shear force applied to them. Wikipedia, of course. And on the left in the blue is a fluid that's got a very low viscosity, deforms very readily with an applied stress. On the right is a fluid with a higher viscosity that deforms less readily under the same stress. The stress here in both cases being gravity acting on the mass of the fluid and resists the container. Viscosity has a wide range of values. The viscosity, we measure it in poise. Don't ask me what the units are. I can't tell you if that's grams per centimeter per liter or what. I don't know. But air has a viscosity of 1/10,000th of a poise. Water has a viscosity of 100th of a poise. Molasses has a viscosity of about 100 poises. Basaltic lava, people have stuck paddles into lava flows and stirred them, and how much work we have to do that. It turns out aren't that only 10 times more viscous than molasses, which I find amazing. That viscosity does depend on how hot the lava is. If it's hotter, it's runnier, how many crystals it has in it, how many air bubbles, because both of those stiffen things up. Glacier ice is quite a bit stiffer, but many of us have some mountaineering in our background and know that, yeah, ice flows. I put an asterisk here because ice is a very funny thing. How easily it flows depends on how hard you push it. The behavior is nonlinear, and the harder you push, the relatively softer it gets. And the Earth's mantle, that orange rock that Martha was holding up, turns out at 1,000 degrees C and under pressures of found 100 miles down, flows very slowly, but flows with a viscosity in most parts of the world of 10 to the 22nd poise. Under Puget Sound, it's a little lower, 1,000 times lower. This is an incredible variation in magnitude. And to compare something maybe we can grasp, the ratio of the viscosity of molasses to the viscosity of mantle under Puget Sound is the same as that of 1 second to the 4.5 billion years old that the Earth is. This is, for me, one of the joys of geology, is getting to think about things that are so different. So the first fluid, the Earth's mantle, which flows and is the cause of the rain shadow. And this is not a geologic map. This is a map of rainfall. And these are not the mountains. This is the west slope of the mountains. The divide is here. And you need to read the legend. The west side of the Cascades is inordinately wet. It's 3 to 5 yards of rain a year country. When I was in college on a Forest Service fire crew, we laughed at our buddies who worked in Vermont over the Still side. That was the valley of no cheer because they never got any overtime, no fire pay. But water comes off the Pacific Ocean, carried by the prevailing winds from the west to the east, hits the high ground of the Olympics and the Cascades, rises. The less dense air can dissolve less water, and it cools off, and it rains. Comes over to the other side of the mountains, and water's been wrung out of the air and it's dry. So we have this amazing contrast between the wet side. Seattle gets a yard of rain a year. Foothills get 3 to 5 yards. Wenatchee gets 10 inches. It's a desert. And that's there because of flow in the Earth's mantle. So what's the mantle? We think of the Earth as being simply layered. There's an outer crust. And beneath that, a mantle that's got a different composition. It's denser and it's underneath. And then the core, which the outer part of which is fluid, circulates, makes a magnetic field, the inner part of which apparently is not. The mantle is more than 4/5 of the volume of the Earth, and it's clearly a rock, as best we can tell. It passes seismic waves like rocks do, but there's lots of good evidence that on a longer time scale, it flows. And if you want to know what the stuff is, mostly from its seismic characteristics, we know that the mantle is brutite, which is this green rock here. And it's a rock made mostly of olivine. Olivine, when it's really nicely shaped and formed, is peridot, the gem, and why the rock is called brutite. If you take what we know from laboratory experiments of the physical properties of brutite and imagine a box that's 3,000 kilometers high and this wide, and a box that's heated at the bottom because the center of the earth we think is hot, a box that's cold on top because the surface of the earth is radiating heat out into space, and a box full of stuff that's heated in the middle because everything's got a little bit of uranium, thorium, and potassium in it, and radioactive decay makes heat. And ask what happens. The answer is the stuff in the box heats up. As it heats up, it becomes less, it expands, it's less dense, it rises, it cools the top, cools off, becomes more dense, and sinks. And that process creates convection. And this is an attempt to model convection in the Earth's mantle. Now, it's not a very good attempt because the Earth's mantle is not a rectangular box. It's the outer 6 layers of an onion. But this is computationally easier. And this is done with what we know of the physics of olivine. I don't know the time scale, but my guess is this is repeating, maybe 1 billion years each cycle. This takes a while. There's no turbulence involved. This is a very stiff fluid. It's a laminar flow. Anyway, that's what we think the Earth's mantle is doing. This is an attempt to do an Earth-shaped model. And I won't pretend to explain all the things that the model is trying to explain, what it shows, but this is a serious scientist who's got a serious computer time bill, who's trying to simulate what's happening in a fairly simple Earth and how we see some of the things we know from the geologic and geophysical investigations. And the repeat time on this one is 7 billion years, more than the age of the Earth. But again, serious scientists think that the inner parts of the Earth are slowly churning by convection. The Earth's a big heat engine. It's giving its heat up into space, and the process of doing that makes everything else happen. This is a surface view of the Earth over a much shorter time period. This is the last 150 million years. It's quite appropriately Afrocentric. It's the center of the universe, the center of the Earth anyway. And it's showing the tectonic plates on the surface, the cold scum on top that's being rafted about by the circulating mantle underneath. And you may be able to figure out that we're over in this area in here. But this is a reconstruction of plate motions over the last 150 million years, plate motions that are driven by the circulating mantle underneath. Now we can bring that home and make it a little bit more local. This is a computer-generated image from topography and bathymetry acquired by traditional, that is, from the last century and earlier surveying techniques. This is people with sonar in ships, with tape measures and theodolites on land and aerial photographs, making lots and lots and lots of maps that later got digitized and turned into digital elevation models. And then I could sit down at the computer and make a pretty picture. But there's no space age magic in here. And this is an image of the Northwest, and the shoreline is this very subtle green to blue transition in here. And this is roughly the US-Canadian border through here. And we can look at it and you can see subduction happening. To make that clear, here's a cartoon of the subduction zone. Many of you have seen cartoons like this and know them, showing mantle circulating underneath here, carrying a scum of the ocean floor, the ocean crust on top of it, that's convecting, being carried underneath the North American plate, which is another thick crust on top of the mantle. As the ocean floor goes down, it's basalt that formed at a mid-ocean ridge and then got wet. And it's also absorbed various minerals out of seawater. And it goes down, it heats up, and the wet basalt melts and makes magma that rises into the crust and eventually erupts as volcanoes of the Cascade Arc. And to relate this cartoon to the map on the left, connect the dots for Seattle to Seattle. The cartoon is where we're California looking north into British Columbia. Here we have a corner of the mid-ocean ridge in the cartoon. It's the same location out here. And you may be able to see these ridges here, stripes. Those are essentially growth rings as the ocean floor is splitting apart from the ocean ridge and spreading. And the subduction zone, the point at which I'm having a hard time with this, excuse me, which the seafloor goes beneath the continent, where that fault hits the ocean floor is the tip of the subduction zone, is this change in slope through here. And right now, the Wenatchee plate, which is this piece of ocean floor out here, is crawling underneath North America, heading off to the northeast at about 2 inches a year. And it's why we had a really big earthquake. What's it been? 300 years ago now, 343 years ago, and why we'll have more of them. This is the same cartoon with some more detail, but we've changed our perspective. We're now standing in British Columbia looking south towards California. And talk a little bit more about as the subducting plate goes down, it melts, magmas rise up, which erupt as volcanoes and volcanic ash. Many of them don't make it to the surface. They congeal in the crust and they form granites like the Mount Stewart batholith. And the granite is a relatively low density rock. The subduction process, the downgoing plate, also has associated with it a stirring of the overlying mantle, which circulates in this fashion. And that creates thermal erosion of congealed mantle at the base of the overlying crust and removes dense material from that. So the crust floats up a little higher. And the two processes together, the addition of low density granite magma and the loss of high density congealed mantle at the base of the crust, result in a mountain range in the Cascades. And it's because of this subduction process, these two things, magmatic intrusion and thermal erosion, we have the rain shadow. The rain shadow. That's a really nice story. There's a problem here, and I don't have a resolution. We know the Cascades have, subduction's been going on for the last 40 million years. There's some fairly good evidence the rain shadow is less than 8 million years old. And the evidence I can't speak to well because it's about plants that I don't know. But you can go dig out a paper by George Musto, who finished his master's at Western a few years before I did, got a job as a departmental technician, and has a publication record that's the envy of most of his professorial not peers. He's a very good geologist. And Estella Leopold, who's the daughter of Aldo Leopold of San County Almanac fame, who spent her career at the University of Washington as a palynologist, an expert in fossil pollen. And they looked at pollen in rocks from about a dozen places across the Northwest, on the west side of the Cascades and on the east, from rocks that were 12 to 2 million years old. And they found that in the 12 and 8 million year old rocks, the pollen was the same on both sides of the range, no indication of drying out. This diagram over here is the kind of evidence they produced and made sense out of. And I say I don't read that well. All I look at it and see, oh, 3 million years ago, sagebrush became much more common. And that's the most I can get out of it. But George and Estella say that the pollen tells them the Cascade rain shadow is a relatively young thing, and I believe them. So we have to ask them, why is it subduction's been going on for 40 million years, and the rain shadow produced by that subduction is only 6 or 8 million years old? Good question. On to the second fluid. Basaltic lava is obviously a fluid. Here we're in Mauna Loa looking at a young active flow. It's pretty cool. It's especially cool when you're looking up at the lava stream up there and it's carrying big boulders of frozen lava, of rock in it. And you know that that boulder lodges in the right place. The stream's going to jump its banks and come flowing down on you. It's quite impressive. This is a view from Wenatchee looking to the northeast at the edge of the Columbia Plateau a few weeks ago. And the top part of this, above the red line, are the eroded edges of basalt flows that come to a basalt group. And I don't know how many flows are up there. Do you know, Ralph? I think it's on the order of a half a dozen, maybe fewer. But they're representative of a pile of basalt that as you go east and southeast gets thicker and has up to 300 flows in it. And this is a pile of basalt that stretches from Wenatchee to Spokane to Lewiston, down into Nampa locally, west towards Prineville, and for that matter, Portland out to the sea. A vast stack of frozen puddles of lava. And here's a map that shows very roughly the approximate extent of this pile of lava. And we're sitting over here. And that picture was taken looking off in this direction. The south margin of this is especially quite inaccurate because there's some complications in deciding what's part of this basalt pile and what's not that I'm not fully mastered. But we know that at 16 million years ago, the basalts erupted in eastern Oregon. They flowed downhill and puddled in the Pasco Basin. They flowed through a low spot in the Cascade Range, east of Portland, which says, wow, there's a Columbia River to make a low spot in the mountains. So we have a sign of the ancestral Columbia at that point, at that time. And they flowed, and they flowed west then into the ocean west of Portland. And we know that because in the hills of the Coast Range west of Portland, we find the basalts interlayered with marine sediments. So they've gone into the water. I apologize for how messy this diagram is. I have to look at it pretty hard. This map here on the right is the same map as we showed earlier, but the basalts are broken up into different age groups. They're a stack of different sub-basalt units from the Steens, the Imnaha, the Grand Ronde, the Wanapum, the Saddle Mountains. And the Grand Ronde is by far the most extensive. It makes up about 3/4 of the volume of the whole stack. On the right here is a diagram showing recently measured ages of volcanic ashes interbedded with basalt. It's hard to date basalt, it's easy to date volcanic ashes. And on the vertical axis is the age that's been measured on those volcanic ashes interbedded with basalt. And on the horizontal axis is the stratigraphic stacking, layering of the basalts. And so if everything works, we ought to see a line going up and to the right. And the observations do that. Hooray, it works. And the important thing, the take-home message here is the Grand Ronde basalt, which is 3/4 of the volume of the province, of the basalt province, was erupted in 500,000 years. Sorry, 500,000 years, from 16.05 to 16.55 million years ago was the eruption of the Grand Ronde basalt. That's 150,000 cubic kilometers of basalt, 500,000 years. That's 10 trillion dump truck loads, or if I did the math right, a dump truck load every second. It's an astounding eruption. And when I have a chance to drive from here to Goldendale or here to anywhere to the south, to the east, I'm sort of amazed. This is world-class geology. It's spectacular. And I'm kind of glad I wasn't around to see it. And you should know, this study was done by people wanting to do paleoclimatology to understand the dynamics of our climate. We know that at about 16 million years ago, the Earth got warmer. And the question is if the carbon dioxide that was associated with the eruption of basalt, liberated with it, might have been the cause of that warming. And the answer was yes, it could have been. The timing is right. So here's our map. And the question here is, where's the Columbia River in all this story? We know that it went through the Cascades about where it goes through now because there was a low spot the basalt flowed through, and it's still there now. To the east in the Pasco Basin, we have no idea where the pre-basalt river was. The evidence is down there buried in the basalt flows. But it's pretty clear that at the northwest corner of the plateau, from Wenatchee over to Fort Spokane, the junction of Spokane River and the Columbia, the basalt flows pushed the river out, and the river is now at basically the former edge of the basalt flow. And it's because of these eruptions, the river is where it is today in this part of the plateau, this part of the state. And there's some consequences for that relate to plant life. First, we have lots of water for irrigation and the power to pump that water uphill. So if you're growing something for profit, good place to be. Second, the river being here, the rivers have basically an infinite capacity to cut down. And so they tend to stay in place as mountains rise around them. And if the rivers here and the Cascades are rising, it means we've got, and we're in that zone of uplift, it means we've got a deep canyon because the river's going to keep cutting down as fast as the Cascades come up. And so we live in a land of steeper slopes because of this incision and therefore thinner soils. And we also live in a land where there's much greater variety of hill slope aspect. I mean, the topography is complicated, it's steep. So some sides of the hills face north and are cool and are damp. Some sides of the hills face south and are warm and dry. And that variety, I think, is essentially an effect of the river being forced into the Cascade Range by the basalt flows. And that's, I think, what Art was pointing at when he put that picture in his book, is mountains have complex topography, which means complex habitats for plants. Third fluid is glacial ice. And you can look at this picture of the Bering Glacier taken from space, and it's pretty obvious that ice flows. Again, that texture says something's flowing. It didn't break like a brick. It wasn't a pile of sand. This is molasses or something like that. 16,000 years ago, not 16 million, but 16,000 years ago, snow accumulated in British Columbia because it got colder. It might or might not have gotten wetter. Built up in a big pile and flowed south into the US. And ice from BC flowed south and flowed out the state of Wenatchee as the Wenatchee lobe, flowed south down Puget Sound as the Puget lobe, came down the Okanagan Valley as the Okanagan lobe, and other lobes whose names I forget come down the Sanpoil, the Columbia, and the Purcell Trench. First, I want to look over west of Bellingham at the Lummi Peninsula, because while we're here, there's a piece of evidence for how the Earth works. It's just too good to pass up. And I want to zoom in on the Lummi Peninsula. This image is from non-traditional surveying, newfangled space technology. This is a LiDAR image made by putting a repeating laser rangefinder in a small plane and flying around and measuring how long it takes for the light to go from the plane to the ground and back again. And it turns out that with modern technology, you can do that very, very rapidly. 2,000 to 10,000 times a second when these data were collected back in 2004. We now do it 100,000 times a second. And we can measure that distance, the time, well, to get a distance within a few centimeters. And we can know where the aircraft is from GPS technology within a few centimeters also. That's the uncertainty in the aircraft position. And when you put it all together, you have a technique basically poking through the trees with a yardstick to measure many, 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 many points rapidly and cheaply. And you can get beautiful images of the topography underneath forest cover. And we learned so much more about Puget Lowland and the west side of the Cascades than we knew beforehand. It's not been quite the same revolution on this side of the mountains, but it's pretty cool stuff. Anyway, Bellingham is just the east off this picture. This is the Lummi Peninsula. The ferry to Lummi Island takes off from Gooseberry Point right here. And I look at this, well, one more detail. This here is the sign of a section line road, as is this, cuts and fills across the landscape. So between them is 1 mile for scale. And I look at this and see all these faint bathtub rings wrapping around the hills. And I've sketched out a few of them in light blue. These are fossil shorelines made as the ice sheet went away. And it may take a bit to wrap your head around this. The ice sheet is melting, so world sea level is rising. But here locally, the weight of the ice is gone. And the ice was 5,000 feet thick over this peninsula. It's gone away in a hurry. The weight of the ice had pushed the Earth down into the fluid mantle. When it's gone, it pops back up again. And it's popping up fast enough that even though global sea level is rising, the land's rising even faster. And so sea level is falling at inches per year here. And these fossil shorelines are recording that. And from that evidence, from the rate at which the land pops up out of the sea after the glaciers are gone, it's how we know the viscosity of the mantle, how we know that it's 10 to the 19th poise here in the Puget Lowland, how we know that in Hudson's Bay or Scandinavia, it's 10 to the 22nd poise. We model the physics required for that popping up to happen and extract the viscosity. Anyway, the physics are the same as kids on an air mattress in a swimming pool. Take the kids off the air mattress, it pops up, comes out of the water. Same process. Ice is a rock. And I go back, I pulled it off my shelf, my 1968, it was an old book then, my freshman year geology text in 1970, Principles of Geology, 3rd edition, Gilly, Waters, and Woodford. Rocks are aggregates of minerals, and the mineral is a naturally occurring substance with characteristic internal structure determined by a regular arrangement of the atoms within it. There's their crystals. And this is a picture of glacial ice. I don't know the scale. It's probably a few inches across, but you can see all the blobs packed together. Those are single ice crystals. Ice is a rock. It's crystalline. And yet we saw that it flows. And I want to look now west of Seattle on the Kitsap Peninsula to see some of the evidence for that flowing of ice. This is another LiDAR image. Bremerton is right here. You may be able to see the dry docks for the Naval Shipyard in the LiDAR topography. This is Green and Gold Mountain, which are a lump of hard rock that has not eroded away as fast as everything else. They're almost 2,000 feet high, where most of the rest of this is at sea level or a few hundred feet higher than sea level. And the ice went over the top of Green and Gold Mountain. And this picture shows two contrasting but simultaneous modes of ice behavior. The first thing you certainly see are all these beautiful scratches. And I think of them as the marks the cat leaves when it licks the butter. But you can think of them also as taking a block of sandpaper over something, a soft surface, and all the gouges you make. And they're showing basically the ice slid over the landscape like a relatively rigid block, scraping stuff underneath it. But you can also see that these scrapes, these flutes, wrap around, diverge and converge around the topographic high at the base of the ice sheet. Think of it as like water flowing around a boulder in a stream bed. And they're a clear sign of fluid behavior inside the ice sheet. So the ice is both a rigid block that's also deforming as a fluid internally. Interesting. Now I want to go to northeast of here. Actually, here is right there, the Waterville Plateau. And this is the Columbia River through here. And this is Grand Coulee. We don't have LiDAR topography of the Waterville Plateau. It's supposed to show up in 2 months. I can't wait. But for a little location, again, Grand Coulee Dam is right here. Electric City is located here. Coulee City at the south end of Banks Lake. Pateros, the junction of the Methow and the Columbia. Bridgeport, this is the junction of the Okanagan up in here at Brewster. Bridgeport's right here. And Withrow, northeast of Waterville, on the edge of the ice sheet. And this is from a study by Dory Covenant, who looked at traditional topographic maps and air photos to look at the effects of ice on the Waterville Plateau. And she mapped out ice flow directions in blue. The black lines are the terminal moraine, the place where the ice piled up stuff at its very edge where it melted. And there are also recessional moraines where the ice margin was stationary for a while as the ice sheet melted back and also piled up debris. The red dotted lines are eskers, which are sinuous ridges created by water flowing in tunnels under the ice, dropping sand and gravel. If you're work in this country, that's where you go mine stuff to build roads out of because it's sorted already. And the important point here is that the ice flowed east to Grand Coulee and then stopped, basically right at Grand Coulee Dam, Electric City. And the ice stopped the flow of the Columbia River there and diverted it to the south. And presumably the ice stopped at Grand Coulee because that's where the river trimmed it, river rushing by. If we go back, it's pretty easy to see that the glacial ice diverted the Columbia River at Electric City to erode Grand Coulee. And that may have happened in a few thousand years during the last glaciation, 16,000 years ago. It may have happened over many, many, many thousands of years in many prior glaciations. My supervisor is hot on the notion that maybe it happened 2,000 years only, in which case that's more astounding stuff, but we don't know. The erosion happened during big scabland floods when Glacial Lake Missoula far off the east dumped and made the Brett's floods that most of us know about. But it also happened during regular flow of the Columbia, because between the floods, the Columbia flowed down Grand Coulee also when the ice was there. And the Columbia flowed south via Grand Coulee to Moses Lake, to Othello, to Basin City, and then rejoined, became back to the main stem in the Hanford Reach, just north of Pasco. And that's exactly those landforms, that geometry is what then Bureau of Reclamation has exploited in the Columbia Basin Project, substituting Grand Coulee Dam for the ice sheet. It's a poor substitute. The ice sheet lifted it up all by itself. We've got to extract all that hydropower and pump water up, and can't make water go. I can't afford to put the entire river up there. I mean, you don't do it quite as elegantly, but the water flows south and irrigates much of central Washington, as you can see in the right-hand image. The Columbia Basin Project is only possible because of the landforms made by the continental ice sheet, by flowing ice. The last fluid is air, and I think we'll all agree that air is fluid and it flows. We feel the wind blow on our faces most days if we're outside. And air in this landscape is a geologic agent. And I want to talk very briefly about loess. Most of you have seen dust devils out driving across the plateau. You don't need a dust devil. The air is still full of dust. One of my surprises moving from Seattle to Wenatchee is our housekeeping hasn't changed, but the refrigerator gets dirty faster here. This is a dusty part of the world. And it turns out that dust deposition is common in much of the world. And this is from a review paper by a colleague of mine, Dan Moose, who's looked at what we know about it. And I want to draw your attention to this diagram here. This is looking at a deep sea drill core, where you can go down the core and measure how much dust there is at each interval, because the dust has got distinctive particle size and mineralogy. And you can also extract fossils out of the core and get dates to say how old you are. And so you can put an age on the core and you can measure the dust fraction. And the blue bars are the ages we know were glacial periods. And you can see pretty readily that there's more dust deposition during glacial periods. And we could talk about why that is. I don't know. I'm sure there are theories. Maybe it's a world with less vegetation, or maybe it's a world with stronger winds. Lots of possibility. World with more big floods. Just make dusty floodplains. This is a model of dust deposition during a glacial period, to make the point that much of the world sees lots of dust deposition. That's variable. The model shows dust deposition in the sandhills in Nebraska. It doesn't show it in the Palouse over here, so the model's not that good, but anyway. And the dust fluxes can be substantial. Yellow is 5 to 10 grams per square meter per year, which is 2 to 4 pounds per square yard per century. The red is 40 to 80 pounds per square yard per century. That's significant. And we see that if you go for a drive any place around here that's flat, you see there's a cap of homogeneous light brown to gray porous stuff on top of whatever's underneath. This is loess, and it's windborne silt deposited by means that are not agreed on, such that it's got lots of holes in it. I think it's because it's settling out because it's trapped by vegetation. So an essential part of loess deposition is there's grass or shrubs or something that's got structure to capture, to slow the air down, the dust can settle out, which means it starts life with holes from the vegetation that's rotted out. It may start life with a modest organic content also for that reason. This is out on the plateau where the loess is sitting on basalt, probably flood scarred basalt. But you see the same thing. This is the west side of Wenatchee to foundation excavation. And we've got, it's not the best picture in the world, but this is a flat spot. This is a cut. This is the top of the cut bank. This is bedrock, volcanic rock and sandstone. This is weathered bedrock and colluvium. And it's quite clay rich and not very porous and stays wet. And on top of that is from 3 feet to about 1.5 feet of loess, which dries out relatively well, but we also know holds water, absorbs water. It's a sponge. And loess, with its high porosity and its modest clay content, stores water from season to season, from wet season to dry season, and releases it to plants. If you ask any dryland wheat farmer, I mean, that's how they make it, why it works. Why dryland wheat farming works is because loess is a great water moderating agent. So what do we learn? Rocks flow, albeit slowly. Lava flows, well, obviously. And air, obviously a fluid, is a geologic agent, a depositional agent. The effects of these fluids govern the availability of water to plants in our region. The flow of the mantle has made the Cascade rain shadow. Flow of basaltic lava has put the Columbia River where it is today, made for this deeply incised landscape, and gives us the great variety of microclimates that show up in a lot of biological diversity. The flow of ice made the landforms that we've exploited for the Columbia Basin Project to allow us to turn the desert into very productive farmland. And the flow of air has blanketed north central Washington with water retentive and water yielding loess. Rocks and landforms tell stories. Everything is connected to most everything else. Thank you, Art. Another geological fluid. Ralph.
Did you consider, the radiocarbon changes of groundwater in the aquifers in the Columbia River salt pile indicate a lot, especially the deeper aquifers that was recharged primarily during glaciation, the last one?
Ralph is asking Ralph, this is Ralph Dawes, who knows this. if the radiocarbon ages of deep groundwater, the Columbia River basalt pile, show that recharge, the filling of the aquifers was during the last glaciation.
Have you heard of that?
I'm not familiar with that work.
You add that on, it's more about, I think, the agriculture, because most of that is deep and they have to pump it up as well.
Yeah.
But that was from the glacial, like the Zula floods mainly, but it filled the deep parts of the Columbia River salt pile that had holes in them so it could take water. And they're using those aquifers in places that are outside the irrigation project. And in some cases, they're overusing them and running out. But yeah, so but it fits in.
Yeah.
But it's caused by glaciation.
Yeah. Yeah. Let's not talk too much about the Columbia Basin projects. I start saying things that Martha gets tired of hearing. The notion of the ancient lakes drives me crazy. If you look at an ancient geologic map, like in 1920, there was no water in the ancient lakes. That water is all excess from the Columbia Basin project. And there's much more surface water on the plateau now than there was 40 or 100 years ago. I don't know. I think the wetlands that are so conspicuous in parts of the plateau may have more history than that, maybe longer, maybe natural. The basalt doesn't perk very well. And so there are, where's Bruce sitting? As he knows well, there are parts of the plateau, marshlands that are excellent birding because of that.
Question you mentioned earlier about olivine being in the mantle, one of the mantle.
Yeah.
I know there's places like the Twin Sisters down about Vega where there's olivine.
Yeah.
So could that have squeezed out to do something from the mantle?
The question is whether we do see olivine on the surface, like the Twin Sisters mountain range east of Bellingham, which is part of the North Cascades, could that have squeezed up from the mantle? And I will say that that piece of dunite that Martha's, or peridotite that Martha's, but no, the little one is a piece of the Twin Sisters. So yes. And I think I'm allowed to say, being a certified expert in the North Cascades, that we really don't know how the Twin Sisters got there. Maybe it got squeezed up, maybe it was clipped off by a fault. We don't know. The Twin Sisters is a big chunk inside a mess of very complicated screwed up rocks. And those complicated screwed up rocks are in the northwestern foothills of the North Cascades in the 3 meter, 5 meter a year rainfall country. And the outcrop is really bad except for logging roads. And so we don't really know what's out there very well. And there are rocks, because of their complexity, that don't yield well to our theories. So we can't predict what there is underneath the trees where we can't see what's there. And we just don't know that much. Sorry. Sure.
Is andesite only in the Cascades or also in the Columbia Plateau?
Ralph's going to correct me on this because listen carefully. I do not know rock chemistry very well. Ralph Dawes knows it better than I do. Andesite, pure andesite is a feature of the Cascades and not further east. Many of the basaltic lavas in the Columbia Plateau basalt group, Columbia River basalt group, are actually not true basalts. They're basaltic andesites. They're intermediate in composition between basalt and andesite. It's a small awkwardness we tend to not talk about.
That's true. They skew a little closer to salt than andesite.
Yeah.
So they're kind of following their guidelines and not being andesite. Yeah, pretty much on the plateau. I don't know any.
I don't think there are any true andesites. There's quite a bit of basaltic andesite. And yeah.
Has anybody done any modeling to show how glaciers or the effect that glaciers make when they flow?
Yes, people do that. The question is, do people do any modeling to show how the effects of glaciers as they flow across the landscape? And yes, people have done that kind of work, and some of it's very interesting, and I don't know it very well. But yes, the ice is a simple enough substance we can conceive of modeling its behavior and try to grab most of the physics and ask, how do we make those scratches? How do glaciers pick up rocks? And that sort of thing has been modeled. I know that. Cece.
Well, I'm just gonna make one little commercial on the Art Cooper connection. Native Plant Appreciation Month starts usually in April, but this year we're gonna do it on Friday, which is March 31st. And at 7 o'clock, if you'd like to log in to the WNPS, Washington Native Plant Society.org website, there is a wonderful history of our Cooper that's going to be presented as a kickoff to Native Plant Appreciation Month. And that should follow some of your stories quite nicely.
Yes.
I was intrigued by one of the last photos that you showed in the Wenatchee area of the loess layer in the excavation. And you had I may have learned something. It was my understanding that a lot of the, for lack of a better word, topsoil or the soil that exists around here came as silt deposits from the Columbia River floods. But I'd be happy to learn that there's loess with that as well. So the question may be, how would one distinguish between a silt, a water deposited silt, and a rolling and deposited loess?
The easy way is loess should have no internal layering. And the water deposited silts, unless they've been churned by bugs and roots, should have well-developed internal layering. You can see. A little bit harder, loess tends to have a lower density, but that's hard to judge. That foundation cut surprised me because it's a low enough elevation. You know, why didn't the floods wash away? It's about 1,000 feet above sea level, and the highest floods reached 1,500 feet in Wenatchee, and it's on a hill slope. And I think of loess being gone, but it's pretty clearly loess, featureless, holds water well, gives it up, easily dug, no layering.
I'll go dig some soil bits.
Good, good.
Thank you.
Let me know. Well, thank you all for your engagement. It's been a pleasure to talk to people who are paying attention. It's wonderful. Thank you.
Thank you all for coming. If you have a minute to help load up the chairs, that always makes our setup easier in the morning.
Thank you, Rob. That was wonderful.